Our today lecture is about interatomic bonding. Interatomic bonding is one of the most important topics of material science or solid state physics, and it deals with quantum chemistry, where we apply quantum mechanics to problems related with chemical energy and reactivity of atoms and molecules. The chemical bonding energy of hydrogen was first calculated by Hitler and London in 1927. Before telling you the history, the significance of atomic bonding must be known. Interatomic bonding basically induce the relevant property into materials. If the bonds are strong, materials will be mechanically strong. Just like I give you the example of diamond and graphite in the crystallography section. Similarly, if interatomic bonding is poor, then this means there are some variations or weaknesses at the outermost orbits of the atom. For example, deficiency or excess of electrons. So the deficiency will acquire electron, the excess of electron will lose electron, which will lead towards bonding. So the first thing, why bonding occurs in certain materials and not in others. Certain atoms form bonds very easily, but the others not very easily. This is because of the electronic structure of the atoms. So the driving force to form a bond is related with the electronic structure of an atom. Similarly, the bonds which can be flexible. In the coming slide, you will know what is flexibility and what is rigidness. When the bond is flexible, the materials will allow to bend. But if the bonds are rigid, for example, if you try to bend a material and it instead of bending, it breaks. This means the material is brittle. So that is also coming from bonding. This is the bonding character of a specific material which give rise to certain properties. So as I told you, the chemical bonding energy of hydrogen was first calculated by Hitler and London in 1927. Then the valence bond theory by Slater and Pauling was introduced, and the molecular orbital theory of Mulliken was followed by that. Nowadays, people use density functional theory, and a lot of people are doing research in this area because science deals with theory and experiments both. So if you are performing an experiment and first do or what you say calculate what will happen as a result of this experiment, then it will be saving the resources. It will help you to predict the results, to interpret the results as well. So density functional theory is nowadays popular in this field. Interaction between or among atoms. I'm using the word between or among. Between comes for two, and among means when there are more than two atoms interacting together. So completely filled shell means stable electronic configuration. Stable electronic configuration means that the electron cannot be easily removed and the atom cannot be easily bonded, or the electron cannot be easily accepted because its outermost shell, the shells are filled completely. So neither the atom will be easily give away or get an electron, and the bonding in such atoms will not be that easy. Atoms short of a few electrons tend to acquire electrons, thus tend to form bonds. And this is the driving force for the bond formation, because simply people can ask you many questions as a physicist, as a scientist, that why do bonds form in the first place? So the driving force for the formation of bond is due to the atom's short of a few electrons, or if an atom has almost free electrons, so they can be bound with the other ones. Also, I am again and again stressing upon my students that when we are speaking to students, a slip of a tongue, for example, if I say positive instead of a negative, if I say getting instead of giving away, this may lead you to many confusions. So lecture is very important, but at the same time book is more important than the lecture, because they are thoroughly checked, and such mistakes are errors which we commonly do during the verbal lectures, they can be corrected there. So always read the book, and I am uploading some materials for you regarding bonding, regarding crystallography, regarding the classification of materials which we discussed in the previous lectures. The energy, now look, when a bond will form, when a bond will form by itself, right? The energy of the pair of atoms, if the energy of the pair of atoms after bonding is lower than the unbonded state, the atoms will form bond, because it is decreasing the energy of the system, and energy will be evolved as a result of that bond. But if energy is consumed as a result of a bond formation, then it will need energy to form a bond. The bond will not form by itself. For example, you hold an aluminum foil, or for example iron foil or iron rod in open air, and it is oxidized. This means that the energy of the atoms in the metal iron, I'm not talking of iron oxide, the metal iron, the elemental iron, the energy there and the energy of the oxygen in the environment is more than when they come together to form a bond. So if the energy of the system after bonding is lower than the unbonded state, the bond will form by themselves. And such materials, for example, you say, will be vulnerable for to oxidation. And to keep them pure without oxidizing, you will need a reducing atmosphere. So when people do experiments which involve elemental metals and which are vulnerable to oxidization, they pull oxygen from the environment. People do such experiments in reducing atmosphere where there is no possibility of oxygen to interact or come in the vicinity of the metal. The difference in the two energies, what two energies in the bonded state and the unbonded state, is called the binding energy or the bonding energy of the relevant system. Now, let us go a little bit more towards physics. Potential energy versus internuclear distance. Because when you are talking of the distances between different atoms, you are basically talking in terms of the distances between the center of nuclei of the two atoms. Energy lowers as the atoms go get closer. So the potential energy is inversely proportional to the distance between the two atoms, as you see in the figure. The potential energy goes down until R is equal to R minimum. R minimum is here somewhere. It decreases, uh, goes down when you reach R minimum, and to the reversal of tendency to bond and repulsion start. So common sense says that when two atoms are coming together, they should enter each other, and at the end there will be only one atom. But it is not happening. Why? Because the interaction between the orbitals, the shells of the atoms, don't allow two electrons in the same quantum state. And that is the Pauli exclusion principle. So one thing, that when you reach a minimum R where the potential energy has gone to a certain level, Pauli exclusion principle comes into play to collapse, to stop, to prevent the collapsing of the system. Thus, we are the potential energy, which is a function of the distance between the two nuclei, centers of nuclei, is attractive at short distances and repulsive at large distances, with R equilibrium somewhere in between. This you can call the R equilibrium. So when you reach here, so the atoms are completely bonded and the energy is negative. So when the energy of the system is negative, means minimum, then you will have to give this much energy. If you look into this plot here, you will raise the energy up to here to unlock the atoms. So this energy has been released as a result of bonding, and now to break the bond you will need this much energy to unlock the bond, and that is basically the bonding energy. So the more negative energy means the stronger the bond, and the less energy means the weaker the bond. These are just models. The exact form of potential can be measured from the heat of formation. Yes, this is the experiment. That when you have a system which can measure the release or absorption of energy, then you can know that how much energy was released due to the formation, and you can sequentially monitor that how the energy decreased or increased of the system as a result of particular bonding. When we say radial or central potential, when only are dependent and no directionality taken into account. In the real case, directionality matters and the problem becomes complicated and needs other factors to be included. Here, in the case of hydrogen, you can see that the inter nuclei distance is 300 pm, picometer, and here it's 150, and here it is 74, and this is the R minimum where the energy has gone to the minimum, and here the strongest bond will form. And when you cross this again, the bond will start to break. the atoms will move away from one another, and because of the Pauli principle, because the two electrons cannot occupy the same quantum state. Classically, we write the force between the atoms is minus if it is attractive, and the change in potential at R equal to R1, and it is directional, as I told you, that you have a unit vector ER, which brings directionality into the matter, where ER is the unit vector along the line connecting the two atoms. An atom in a crystal will be in equilibrium when the sum of forces upon it averages to zero over a long time. If you remember, I had told you that atom cannot be at rest. It is always in motion, to and fro motion. But still, when we talk of crystallography, we give exact positions to the atoms. And I told you in the lecture and convinced you that that is basically the averaging over a long time. If I'm moving this finger constantly, so the finger is in this distance always. So I am correct if I give this position to the finger, but over a long time. If my time I am measuring in nanoseconds, so at one point it will be here, at another point it will be here, at the other point it will be here. So over a short time, I am not correct to say that the atom is here, oscillating at this position if I am talking in terms of crystallography. But if I take, for example, in 2 seconds or 1 second, then obviously if this atom is moving, it is everywhere in this position, and that is why we give an average position to the atom. Vibrations makes it difficult, but averaging over a long time for a large number of vibration can give this. And I had given you the example that if you ask about a teacher, that is he in the department, none can say he is in or not. But if you say, ask that can he be in the department in the coming 24 hours, then the answer is yes, because he is moving around, and in 24 hours he will come to the department certainly. The same thing is here, that if at a particular moment where the atom is, it is difficult to say, but over a long time you can average the position of an atom. Now, this was just an introduction that what bonds look like, and just introducing you into the significance of bonding, the structures, the angles which form along different directions in the unit cell. They are all associated with bonding as well.